In this video, we are going to be discussing the frequency dependence of the permittivity. Basically, is there a dependence on the frequency of the electromagnetic wave in some material with a permittivity epsilon. Now, we do know from observation that this is true. So if I take something like a non-conductive material, I don't know, like glass. Glass is a nice insulator. And I make a prism out of it. Then when light shines on it, the light is then going to bend from Snell's law. But if I look at the different colors, then what I get is what's called dispersion. The light now is coming in parallel, and it is going to now bend at different angles. And so I get a nice rainbow effect that occurs. Okay, so we want to see, can we relate the permittivity of that material, like glass, which we can relate the permittivity to the index of refraction, and therefore come up with a frequency or wavelength, a better way of saying it, a wavelength dependence on the material. And then we will come up with an idea for the dispersion of it. So basically a spreading of the light by color. Okay, so what we're going to do is we'll start with the wave speed, which we've already worked out. We can write that down as the frequency divided by the wave number. But if we now have many different waves, well, we get what's called a group velocity. Where if you think about it, I've got a wave coming in here of one wavelength, and they have another wavelength, and another wavelength, and basically all of these waves will now add together and make this kind of group, this wave packet. So each individual wave has its own velocity v, but the entire wave packet taken together moves with a group velocity v sub g. Okay, so now what I'm going to do is try and model the interaction of the electromagnetic wave on the material, and I'm only going to consider electric field. So let's ignore the B field and only look at the electric field. And so what we're going to do is we're going to look at the electric field that is now applying forces to the electrons and the molecules in the material. So we have our material, which is now full of molecules, and then the E field goes through there, and that E field is now going to apply forces on the electrons on the molecules in there. We're only going to consider the electrons. So I'm going to model this as springs. So the binding force of electrons in a molecule is minus some spring constant, the strength of the binding force of the molecule, which I can rewrite as minus the mass of the electron, its oscillation frequency squared, and the distance. So this is the electron mass. This is the displacement. And this is the oscillation frequency, which I can write as the spring constant divided by the mass, square root of the whole thing. Okay. That's kind of an ugly square root, but anyway. But now, not only is there going to be an oscillation as the electromagnetic wave applies forces to the electrons and makes them kind of wiggle, not break the bonding, but just wiggle. But I imagine there's also a dampening force. Due to the electrons bound to the molecules, which are now radiating. So if I'm going to give energy to the electron, which is bound inside the molecule, it may go up to a different energy level and then fall back down and then radiate. And that radiation is going to be basically a loss of energy and therefore dampen the oscillation of the electron bound to the molecule. So we're going to model this as, so this damping force is minus m times some factor gamma times the velocity of the electron now. So dx dt is the velocity of the electron. So you can kind of think of it almost like a frictional force from classical mechanics. So I said gamma is just a factor, which is the strength of the dampening. So whether or not it's a strong damping or a weak damping, we can just throw that in by some number, gamma. Okay. Now the electromagnetic wave is going to apply a driving force. So it's going to come in. So here's my wave, and that wave is then going to have some amplitude. So here's my E field. So those are my E amplitudes. And then what happens is, if there's an electron here, it's going to couple to the field, and it's going to stretch that little spring. Or it's going to compress that spring. Or it's going to stretch it out again. So if these are a bunch of electrons in the molecule spread out in this material, as the wave comes through, it's going to stretch the springs out, compress the strings. Right? So it's this driving force from the electromagnetic wave. And so I can write that driving force as we normally do in electrostatics. It's the charge times the electric field. And in this case, it would be the charge times the amplitude of the electric field times the oscillation of the wave. So omega is the driving frequency. So it's how much that wave is oscillating. And Q is just the electron's charge, since it's that electron which is coupling to the electromagnetic wave. And again, like I said, we're going to ignore magnetic fields. We're only thinking about the electric phenomenon here. Okay, so now let's put it all together. So Newton's second law says that mass times the acceleration is going to be equal to the sum of the forces. So we've got the binding force acting on the electron. We've got the dampening force. And we have the driving force. And all that leads to the electron's motion. Okay, so if we put this all together, I've got if I've got a negative force, like the damping force, I'm just going to move over to the other side. And I've got the binding force, which is also negative because it's a binding force. And all of that's equal to the driving force. Like so. And lo and behold, we have a second order differential equation with a first order term, which, you know, is kind of a nasty differential equation, but it's not like it hasn't been solved before. So it's a good thing that we're making you take differential equations. So anyway, so what I'm going to do is I'm going to switch to the complex notation to make it easier to solve. And so we don't have to worry about the sines and cosines. And so when I do that, I get a complex function, x tilde, is equal to q e naught e to the minus I omega t. Okay. So the last thing I'm going to do is I'm going to divide both sides by the mass just to kind of clean it up. Okay. So now we've got a form which is much more pleasing to the eye and a little bit easier to solve. And so okay, so what I'm going to do is make one last substitution and assume a solution of a time-dependent solution where x has some amplitude x tilde, e to minus I omega t. Doing that, it cancels out the e to the I omega t on both sides, and what I'm left with is I get minus omega squared x tilde squared minus I omega gamma x tilde plus omega naught squared x tilde is equal to q over m e naught. So now I can solve for x0 tilde, which is q over m divided by omega naught squared minus omega squared minus I omega gamma. All of that times the amplitude of the electric field. So it is a complex number because you notice now I have an I down here. But we now have a solution for our function, which we can then plug in. So I'm going to stop here, and I will continue this discussion in the next lecture.